Gavin studied at SUNY Geneseo, and he has a degree from there for both geological sciences as well as adolescent education. So, very interesting career path. He then moved to Gleason, where he got a master in hydrogeology and a PhD in environmental engineering and earth sciences, and then continued his research there as a postgraduate researcher. He joined us last summer and is going to be helping us expand the forensic sciences field. And today he's going to speak to us about hurricanes and wildfires. So what's not to like? Please welcome Gavin.
All right, well, thank you, Sarah, and thank you to the Geology Department for giving me this time slot, and thanks to Ryan and the Biology Department for inviting me to talk. I'll take any chance I can to talk about wildfires and hurricanes and how they impact our environment. And that's because over the past couple years, you may have seen or heard in the news a lot about hurricanes. I don't know if this is on. Okay. Can you hear me now? Hello? Oh. Can you hear me now? Yes. All right, it's like a Verizon commercial for those of you that are old enough to know that. So for hurricanes and wildfires, they have been in the news. They've been hot topic. You may have heard about them. You may have seen about them. But what we also know is that you take in approximately 8 hours of media intake a day. So you're experiencing 8 hours of media intake. That's a lot of information, a lot of time. But we also know that the average person loses interest in a single topic after 9 minutes and 59 seconds. And we also know that the average person, from a study, which you know from Miller's Law, that a person can only have really 7 pieces of information in their working memory. And you might be asking yourself, why am I telling you this? Before I just continue to ramble on about hurricanes and wildfires. Well, if there's any information I want you to take away from today, our key points is that hurricane and wildfires, they are disturbances. They have visual disturbances that are commonly focused on, but they also have invisible disturbances to the environment that are equally important. They're impacting our biogeochemistry, which is biology, our geology, as well as our chemistry, specifically that water cycle and the carbon cycle. And these hurricanes and wildfires are connected. They are related. So climate is driving these events. It is impacting our water quality. Both events are impacting water quality, and both events are also impacting our soil health. So they are both related, even though they are different disturbances. So before we kind of go into the wildfires and hurricanes, we're going to start with some background information just about the water cycle and the carbon cycle. We'll then talk about hurricanes, how they're impacting atmospheric CO2. How they're impacting what is known as blue carbon. We'll take a look at wildfires, maybe what wildfires produce, the types of material wildfires produce, how they can impact our water and our soils, and then we'll talk really broadly about these large-scale disturbances and really how they're driving climate change as well as impacting our water. So to start, we're going to start with atmospheric CO2. So when I say CO2, I mean carbon dioxide, and CO2 can be in a gas state. When it's in our gas state, it's in our atmosphere. And while I'm talking about atmospheric CO2, I'm going to display this little animation here. So to get a lay of land of this animation, to the left we have a plot. This is our globe on a 2D plane. So we have our equator in the center. Our south pole is to the left of the plot, and our north pole is to the right of the plot. And those small dots we see, those are representing atmospheric CO2 monitoring stations. So stations that are continuously measuring the concentration of CO2 in our atmosphere across the globe. And they're measuring the concentration, which is our y-axis, in parts per million. And that information is also going to be displayed on this plot to the right, which is years on the x-axis, so time, and concentration on the y-axis. So we're going to see how concentration has been changing over time. And so what you'll notice as this animation is going, these two plots are stationary, going to display the same information, but our atmospheric CO2 concentrations are increasing at an accelerating rate. They are increasing very quickly, increasing the amount of CO2 in our atmosphere. And so since we started measuring atmospheric CO2 in Mauna Loa in 1950, we have increased from around 320 since that 1950 point to approximately 420 parts per million to modern day. And we can even take this further to take a look at the Industrial Revolution, which happened in 1750. We're at about 260 parts per million during that Industrial Revolution. We increased by 47% to where we are today at that 420 parts per million. We haven't seen these concentrations of atmospheric CO2 in geologic history over the past 800,000 years. So in between our glacial, interglacial periods, where we know we had warming, we know we had cooling, we never exceeded that 300 parts per million, and we never exceeded at a rate that we are experiencing today. But you can see over this time that CO2 is fluctuating in the atmosphere. Even you see small fluctuations in this plot. And that's because carbon is always cycling throughout our environment. Carbon is in the atmosphere. We just talked about atmospheric CO2, but that carbon can be taken out of the atmosphere by vegetation through photosynthesis, stored in our soils below ground, can also dissolve into the oceans or be taken up by algae or other vegetation in the oceans, then be buried below ground in oceanic sediment. So this carbon is always cycling from the atmosphere to our oceans to the soils. It's always going around in this cycle. But why we cared about that atmospheric CO2 and why only half of you heard about it at the beginning of the presentation is because this atmospheric CO2 causes a greenhouse effect. So CO2 is a greenhouse gas, which what that means is our sun is always giving UV radiation to Earth. It's always emitting UV radiation to Earth. Our Earth absorbs that UV radiation, sends it back out as infrared radiation, which is longer wavelengths. And that infrared radiation is then trapped by CO2 in our atmosphere, absorbed by that CO2 and sent back to Earth. So heating up Earth. And that's really the cause of global warming. So the Earth is acting like a greenhouse. Outside of the greenhouse might be cold. Inside that greenhouse, it is warm. It's because the sun's heating up the material in the greenhouse. That material emits infrared radiation trapped by the glass or our CO2 on Earth and then sent back to Earth's surface, causing global warming. And just the sheer amount of CO2 in our atmosphere is really what is causing that global warming. We have so much atmospheric CO2 that is causing that greenhouse effect to be much more intense. So we can release atmospheric CO2 in the atmosphere, and we know that's bad, but we want to try to store that and understand the natural ways that we take that atmosphere or that atmospheric CO2 out of the atmosphere and store it below ground. And that is known as sequestering. We are sequestering carbon and then storing it. And in order to really know that transport from that source emissions in our atmosphere to that sink below ground, we have to understand how the carbons transport, and the main way that carbon is transported is with water. So water is very important to us. The water cycle is super important, and I like this phrase of carbon goes where the water flows. So if you have water flowing somewhere, there's going to be carbon also flowing in that same cycle, combining the two of water cycle and carbon cycle. So what I try to do with my research is take a look at hurricanes and wildfires and how they impact that water cycle and how they impact that carbon cycle to either one, impact our water quality, or two, impact climate change and future climate projections. So I'm going to start with hurricane. So hurricane is just the common term for a tropical cyclone that is occurring in the Atlantic Ocean. A tropical cyclone is a rotating low pressure system that starts in the tropics and then moves up the Atlantic Ocean. And it's a series of organized thunderstorms. It brings immense energy. It brings the storm surge, high winds, high rains, and the IPCC, or the Intergovernmental Panel on Climate Change, in their latest report has projected that tropical cyclones with future climate change will become more intense. So that's important. We're getting more intense storms due to climate change. We have warmer weather creating larger, stronger storms. That means we're going to get more storm surge, higher winds, more rain. Well, we also know that these storms are impacting our coastal setting, and on that coastal setting, we have an environment known as a tidal wetland. And these tidal wetlands are extremely important to carbon cycling. So tidal wetlands are able to sequester atmospheric CO2 with primary productivity. So through photosynthesis, the vegetation is able to take CO2 out of the atmosphere. It is then putting it below ground with high sedimentation rates. So tidal wetlands are these coastal sponges. They're absorbing sediment. They're taking CO2 out of the atmosphere, storing it below ground with high sedimentation. Then once it's below ground, they're also anoxic environments. So there's low decomposition rates. The carbon isn't being consumed. It's going to be stored for a long period of time below ground and out of our atmosphere, which is good. And so these environments are extremely efficient. They're estimated to store more carbon per unit area than forests at rates of 30 to 50 times faster. And they also are estimated to sequester about 116 teragrams of blue carbon per year, which equates to about 61 million pickup truck loads of blue carbon per year. And so that leads to the question, if we're having more intense hurricanes, they're hitting our coasts. If they hit these tidal wetlands, what are those hurricanes going to do to the carbon cycle in those tidal wetlands? How will they impact the carbon? So we're going to take two different approaches to look at this. We're going to look in the modern time. When a storm hits a coast today, what happens with the carbon? And then also we're going to try to take a look at this historically and turn on our geological brain to think about, in the past, what can we learn from the past? And information is important because our main governing body for climate change, the IPCC from the United Nations, is telling us that tidal wetlands are important. They do store CO2. They may also have CO2 be emitted, but they don't currently account for that in their climate projections because of lack of data, lack of knowledge. So we're trying to really help the IPCC with understanding how these important environments are cycling carbon. So in the modern time, I built this, what I call a soil gas well, to measure CO2 gas that is emitted from the soil. So it's carbon that's in the soil and then becomes in the gas state to be emitted to the atmosphere. And how we measure that is with CO2 gas flux. So a flux is a change in concentration over time. You multiply that by the ideal gas law, and you have that over a known area of our well. So for our system, we have a sensor in our well. It's measuring that concentration over a given amount of time, and we have our known area of the well to see CO2 gases fluxing from the soil. But in a tidal wetland, we have to take into the consideration of surface water for the fluxes. So we're in a tidal wetland, so we have to account for our surface water. So we built the system to be able to float with rising tides as tides come in and sink when those tides go down. Our sensor is protected above water, so it's not damaged to collect those CO2 concentrations. And it is also a pretty strong system to withstand those hurricanes. They're high energy systems. When they're coming in, we want to be able to collect concentrations throughout the extent of the storm. And these systems are also normally in remote locations. Tidal wetlands are difficult to navigate and get through. So our systems are connected to a cell tower so that we can collect our data in real time. Also, just in case our system gets blown away, we can then know what the data looked like before the system got washed away with the hurricane. And for the data that we'll look at, we're going to look at net flux. So adding together all of those flux calculations that we're completing with those measurements. And for those net flux calculations, if it is a positive value, that means that the system is fluxing or emitting CO2 to the atmosphere. And if it's a negative value, that means that CO2 is being absorbed by the environment or being sequestered by the environment. And lucky for me, I deployed these stations in the North Inlet Winyah Bay National Estuarine Research Reserve, which is managed by the National Oceanic and Atmospheric Administration in Georgetown, South Carolina. And I was probably the only person who thought I was lucky to be hit by Hurricane Ian, which was a Category 1 storm that came through. And you can see how the environment changed with these photos that were taken in real time. This is the wetland prior to Hurricane Ian. This is the wetland during the peak of Hurricane Ian. So bringing in storm surge, rain, winds. And it went directly through our study site. And during that landfall of Hurricane Ian, I collected CO2 flux measurements for about 4 weeks prior to Hurricane Ian, during the extent of Hurricane Ian, and 4 weeks after Hurricane Ian. And if you zoom in, we have our regular raw CO2 concentrations applied to that flux equation. You can zoom in to closer values to see specific time periods, so 72, 48, 24 hours before, same time period afterwards. But these are just a lot of information, a lot of wiggles. We're collecting a lot of data to try to really understand that CO2. And if we apply this to that net flux equation to kind of get a more broad view, we can calculate on each day over a 24-hour time period, was the system generally emitting CO2 or was it generally sequestering CO2? And we can also add those up for weeks prior to and weeks after Hurricane Ian. And so on a daily basis, the environmental systems change. The system could be emitting one day and then sequestering the next day. But generally, over the 4-week period prior to Hurricane Ian, we are generally sequestering CO2 in North Inlet in South Carolina. And then during the 24-hour period of Hurricane Ian, we're sequestering CO2 again. And then following Hurricane Ian, our system started to emit CO2. And so to give a brief kind of summary of that, prior to Hurricane Ian, for those 4 weeks, we're sequestering CO2. It's going into our soils. Oops. During Hurricane Ian, that 24-hour period of Hurricane Ian, we're sequestering. Oops. Technical difficulties. And then post-Hurricane Ian, we are then emitting CO2 for 24 hours. So that is kind of a broad view of a long time period prior to Hurricane Ian. If we want to just worry about Hurricane Ian itself, how we measure hurricanes, before I said it's a low pressure system, we can take a look at when the pressure starts to change in the environment. So we're also collecting meteorological data. So in the environment, when this pressure starts to drop, that means the hurricane is coming onto land. The eye of the hurricane is coming onto land. We can take a look at what the CO2 flux is occurring then. So when the storm is coming onto land and the storm is falling on land, we are emitting. Once that eye passes the system, the pressure starts to go back up and we are sequestering CO2. But over the course of the eye making landfall and then moving inland, it was a general emission of atmospheric CO2. And we also know that these storms bring in water. So as the storm comes in, those water levels are going to rise. As those water levels rise, we can see what's happening to the CO2. As the storm moves inland, those water levels will go back down to normal conditions. We can see what's happening to the CO2. So as water levels rise, storm made landfall, we're emitting CO2. As the storm moved inland, we started to sequester CO2, but over the whole course of the storm coming inland, rising waters, and then those waters went back down, we were generally emitting CO2 during the storm itself. So again, quick summary of the storm of Hurricane Ian. When Hurricane Ian made landfall, we were emitting CO2. It was bringing a lot of energy, churning up those soils, emitting CO2. Once the storm went inland, things started to settle down. We were sequestering CO2. Over the whole course of the storm caused general emission of CO2. And so we don't only want to worry about just when the storm is happening. We want to think about this environment. The environment's going to stay there. So what were the lasting effects of Hurricane Ian on that environment? So we know that over the 24-hour period of Hurricane Ian, we were sequestering CO2. So sequestering, remember, is going to be those negative values. We got to go below 0. But after Hurricane Ian, our environment didn't go back to a net sequestration until December 22nd. So the landfall happened on September 30th. So about 3 months it took for the system to go back to its net sequestration. So for the system to recalibrate itself and get back to that net sequestration. But it is also important to note we did have some equipment maintenance, so we do have some data gaps in there. But with the data that we have, it took 3 months for the system to recalibrate. So in summary, what we learned about Hurricane Ian in the modern time is that Hurricane Ian came in, it brought a lot of energy to the system, and that energy that it brought to the system churned up some sediment, churned up some CO2, and released it to the atmosphere. So that's what we learned from studying Hurricane Ian in real time. But again, if we turn on our geology hat and we think about, we learned this in the real time, but there's been a lot of hurricanes, there's a lot of tidal wetlands. What can we learn from past storms? So those tidal wetlands were emitting atmospheric CO2, but can they also store atmospheric CO2 following a storm? Can we see that with past events? So our approach to do this was to collect sediment cores, taking a drilled core out of the ground and analyzing that sediment to try to tell a story of past hurricanes by taking a look at carbon concentrations in the sediment, taking a look at particle size, radiographic imagery, and isotopic analysis. So our goal with those sediment cores is to, again, tell a story of past storm events and what was happening with carbon during those storm events. So to do that, first we have to figure out the carbon concentration in the soils. To do that, we do elemental analysis. So we combust our soils and we measure the percent carbon within those soils. We also use particle size analysis. So we know the carbon concentration, but we have to find a storm. And when storms come, they bring that water, like we talked about, high energy flows. They're going to be able to carry larger particles. So we're going to look for those larger particles in these generally fine-grained tidal wetlands to indicate a storm. We're going to try to back that up with radiographic imaging, so taking X-rays. Again, those large flows can carry dense material, bring those dense material to those tidal wetlands, which are usually fine-grained. An X-ray shoots X-ray beams. If you're thinking about the ones you get in the hospital, they go through your arm, your dense bone collects the X-ray beams. We're going to do the same thing, but with our sediment cores to try to find dense material to indicate those storms. And then also isotopic analysis to get an age date of the material, to age date that storm, as well as determine a sedimentation rate for us. So what we have to do is take a look at our peaks. So we have our percent carbon, that is down core. So here is our sediment core. We have our percent carbon, how much carbon is in that sediment. We're looking for high peaks. That means we have a lot of carbon. We also need to take a look at our grain size and compare that. Do our peaks of high carbon correlate with peaks of larger grains, indicating that maybe there was a storm that came through, brought those large grains, and also brought some carbon with those flows to be deposited in the wetland? And then do those peaks also correlate to radiographic images? So we found potentially 4 events that could show this correlation. But really what was interesting that we found is as we are looking at if we're finding these changes in carbon concentration, coming with sediment that's going with these large flows, we're trying to figure out that carbon storage or the carbon accumulation rate. If we can take our carbon concentrations and compare those to the sedimentation rate, we can see approximately how much carbon these wetlands are storing over a given amount of time. And the East Coast range for tidal wetlands for the carbon accumulation rate is between 25 to 155 grams of carbon over a squared meter per year. So that's a pretty big range. These tidal wetlands are differing greatly along the East Coast. And what we found in our environment from the two places that we took sediment cores is closer to the inlet of the tidal wetland at Town Creek. And we took a sediment core over towards Winyah Bay at No Man's Friend Creek on the outskirts of the tidal wetland. And what we found is there's only a 3.4 kilometer distance between these points, but they differed greatly in their carbon concentrations and their carbon accumulation rates. So this location at No Man's Friend Creek had a very high sedimentation rate. It also had a lot of carbon. And we hypothesized this because No Man's Friend Creek's watershed is 47,000 square kilometers. It is the second largest watershed on the East Coast after the Chesapeake Bay. That means it's bringing a lot of terrestrial carbon down to the wetland, being deposited in the wetland with high sedimentation rates, pushing that carbon below ground. Compared to Town Creek, has a much lower sediment accumulation rate, and we also see a lot lower carbon concentrations. It's pulling carbon from a lot smaller watershed, not able to get those carbon concentrations and not able to bury them with the sedimentation. So what this tells us is that carbon accumulation may come with high sediment loads, may be buried below ground with those high sediment loads, and our tidal wetlands along the East Coast are differing greatly because of that, and they also are differing greatly within our singular tidal wetlands. So if we summarize that, high energy storms may induce carbon transport. As those storms go inland, they may pick up that carbon, may pick up that sediment, bring it down to the tidal wetland with high sediment rates, push that carbon below ground to store it. And this is happening very differently depending on what tidal wetland you're in along the East Coast, as well as those specific tidal wetland environments have different carbon accumulation rates within them. So overall, the key takeaways we have from this hurricane and carbon transports, as well as the water cycle, is with modern hurricanes, these modern hurricanes are bringing high energy. Those high energies may cause a quick change in the carbon cycle, emitting CO2 with the high energy of the hurricane. And then following hurricanes, if we use our sediment cores, we can think that if there's flooding inland, bringing carbon down to the coast, burying it with high sedimentation rates, our wetlands may be storing more carbon after the hurricane event. And we hope to use this information to really better understand how these environments are working, to understand if we have more hurricanes, how is that going to impact the carbon cycle and future climate as well. Okay, and we're going to just transition quickly to cover wildfires. So wildfires are large-scale disturbances, just like hurricanes. They are producing smoke, they're producing these hot flames, they're changing how the environment looks. And might even, you could remember on the North Shore last fall, waking up and seeing the smoke in the sky, maybe smelling that smoke. These wildfires are producing a big change. And the reason why these wildfires are occurring is due to the water cycle. So we have drought conditions, warm conditions, not a lot of water, allowing sparks or embers to create a wildfire. And when that wildfire occurs, it's going to change the soil chemistry, the microbes in that soil, as well as how water reacts to the soil after the fire event. So that drought condition led to a fire event. That fire event is then going to change the soil chemistry. So the combustion of the fire is going to impact the chemistry of that soil. By impacting the chemistry of the soil, you're going to change how the microbes are reacting in the soil to that environmental change. And then following after the fire event, you're changing the chemistry and the physical structure of the soil. So you're going to change how water reacts to that soil. Water is going to react differently of not infiltrating or going into the ground, or maybe it increases its overland flow and flows over the surface, carrying that fire material to local water sources. And if we come back to our friends at the IPCC, they tell us that with climate change, we're going to have more compound heat events and droughts, and that's going to lead to more increased and intense fire weather. They also tell us that with climate change, we're going to have larger and more intense precipitation events. So if we're having increased heat waves and droughts, it's going to lead us to more fires. And if we're having increased rain events, heavy precipitation after that fire, what is that going to do for the carbon cycle as well as the water cycle? So that kind of led to our objective is how do wildfires impact the composition as well as the production of carbon in environments, as well as once that carbon is changed due to the wildfire, how is it then transported within the system? So we have three different working parts. We have our fire, that's going to change the solubility, the chemistry of the carbon. Is it more soluble? Can it get into that water after the fire and be transported, or is it going to stay in the system and be insoluble? So if the fire is producing ash, that is generally soluble. If it's producing charcoal, that's generally insoluble. And then infiltration, so how water is going to move that carbon afterwards. So if it's an ash-like material, it's going to allow infiltration. It's going to allow water to flow into the ground. But if the fire is producing a lot of charcoal, it's going to produce that overland flow, making water not go into the ground, causing flooding going down to a local water body. And then finally, if we're changing that water, we're changing that chemistry, we're going to impact the microbes as well as the overall ecosystem and the overall water quality. So to study this last fall, I was involved in conducting high-intensity prescribed fires over a whole watershed. So the reason that we're doing this is we're trying to use prescribed fires to not have future fires, but also for a science aspect to understand how those fires are impacting the system. And we wanted to do this at a watershed scale, not in a lab, making sure that we're getting actual measurements out in the environment. So we conducted two high-intensity prescribed burns in South Carolina in the Clemson Experimental Forest and at the Savannah River National Laboratory. And so they were really intense fires. And what we did with these fires is prior to the fire, we collected infiltration measurements to see how water infiltrated into the environment naturally. We collected soil cores to get the natural chemistry of the soil prior to the fire, as well as surface water samples. And then we had a prescribed wildfire event. We went through and we did all of the same testing along with measuring the fire. We measured how severe the fire was as well as how hot the fire got. And then we can compare now our pre-samples to our post-fire samples. And why this is important is because you generally don't know where a wildfire is usually occurring. So you can't get a pre-control sample to really know the full effects of the wildfire on the environment. With this study, we were able to get that control pre-sample to be compared to the post-samples. And since we know there's going to be more precipitation, we also took samples after a few rain events, as well as simulated some rain events to really see how that carbon's transporting after the fire and after the rain. And so right now we're in the process of doing a lot of lab work, identifying that carbon, so identifying total carbon concentrations. We're also trying to characterize that carbon. Is it a normal natural carbon or is it a black carbon? Was it produced from the fire? So we're doing this work with really high-level analytical equipment at the Pacific Northwest National Laboratory. There's only 2 FTICR instruments in the US. One's in the Pacific Northwest Laboratory in Seattle, and the other's in Florida and Jacksonville at another national lab. We're also doing photobiodegradation studies. So once the carbon's produced, we introduce it to microbes to see how those microbes break down that carbon, as well as taking a look at how the microbial communities are reacting post-fire. Are certain species or certain types of microbes becoming more abundant in the environment due to the fire? And then I moved to New England last fall, and wildfires followed me to New England. We had some local brush fires. So during this local brush fire, we took the opportunity, and a couple students came out to sample some soils. It happened right behind the Walmart that's on Highland Ave. There was a pretty decent sized brush fire that was pretty intense. You can see by the ash that it produced. We went and we collected some soil samples, and we're planning to process those soil samples to see what type of carbon was produced, maybe what type of toxic metals were produced. Fires can also produce metals in the environment. And what is interesting about this fire in this location is that there's a very steep slope behind that Walmart down into this body of water, Spring Pond, which is a natural drinking reservoir. So whatever was produced during that fire with the water cycle has the opportunity to at a later time be picked up and brought down to that water body. So overall, our key takeaways with fires: with climate change, we might have an increase in fire weather and fire activity. We also, with climate change, might have more flooding due to high precipitation events. So fire events, they change our soil. They change how water flows over the soil. They change the chemistry of our soil, producing different types of carbon, different types of metals. They also impact how our microbes can break those constituents down. And then if we have rain events, that's going to impact that transport of those metals and carbons to our local water bodies, and that's going to impact our local drinking water. So I just gave you a bunch of information, even though I know you stopped listening after 9 minutes and 59 seconds. So the key takeaways again, we did a bunch on the water cycle, carbon cycle, talked about hurricanes, talked about wildfires, how it impacts climate. But if you can take anything home, water is precious. It's one of our most precious commodities. The water cycle is closely combined with the carbon cycle. So water on Earth and climate are closely related to one another. The IPCC is telling us that wildfires and hurricanes are going to get worse, and that is going to impact our water and carbon. And we need to continue to study that to know how to react to those changes that are happening with climate change and in our environment. And I would be remiss to also not bring this up right now too, as I have a captive audience. So all of the methods we do in environmental science of collecting field samples in the liquid state, gas state, solid state, doing laboratory analysis on them is very similar to processes you follow in forensic science. So if you're interested in that type of lab work, that type of field collection, we have a forensic science program in the geology department. If you scan that QR code, it'll bring you to our page to take a look at it. Yeah, so that is a great question. So that pH change, there is generally a pH change. What I am more concerned about with the pH change is how it changes metal speciation in the water. So pH will change how the chemistry is occurring, which can impact the production of different metals, some toxic, some non-toxic. So in terms of pH, if pH does change, it usually becomes a little bit more acidic after the fire.
So that would be the mobility of the toxins.
Changing the mobility, yep. Yeah, absolutely.
Thank you so much. Thank you.
Yeah.
You showed us that during a hurricane event, the wetland goes from a sequestering cycle to an emission cycle, and the system didn't recover for 3 months. And you also told us that over time we expect to see more hurricanes. At what point these wetlands will not be on a net balance sequestering any longer? How many hurricanes does it take to balance it?
That's a great question. That is why we need to put more of these instruments out and more wetlands to see, and why we did that extended 4 months to really see how the system reacted and came back to normal state. I can't give a definitive answer. That was the only hurricane I was lucky enough to get, but.
you for your talk. I don't know if this is working.
I have experience with that one. I don't think it is. Yeah.
I was wondering what causes, if you know what causes the sequester or the emission after the hurricane. Is it that sediments are exposed, or like what's causing that net emission?
Yeah, that's a great question. From what I understand is that that energy is churning up that sediment. It's taking that carbon that is stored below ground, allowing it to then be kind of then reused again in the environment, allow it to be emitted. So this usually low energy environment, storing things with high sedimentation rate, is basically churned up and then released again. Yeah?
Is the sequestering of carbon occurring primarily due to just carbon dioxide going or inorganic form and getting stuck in the sediment, or is it the organisms that are biologically sequestered?
Yeah, it's twofold. Both of those are happening at the same time. So what we were measuring is technically the inorganic going down into the system. Total carbon, when you're taking those sediment cores, would be both of inorganic
so
and going.
When the hurricane goes through, did you look at what is affecting the grasses and so forth, and the dunes and the algae and the surface? What kind of events?
Yeah, that is, I am not the best biologist, so I did not look at that, but that would all impact the overall carbon cycle and sequestration.
Gavin, thank you. I have a question, general opinion, actually related to that hurricane event. So based on your talk, you have one particular location, one particular hurricane, and then, I mean, we have the same problem with geology all the time. We look at the modern, but we need to have as many as examples we have, so we have some generalization to look at the geological record. Do we have just one event that you make conclusion and look at the whole geological record, or do you see this in other places as well?
You do see these changes in increased carbon storage in soil cores. So I created that system to measure CO2 flux in modern time. The normal way to measure it is with a chamber that's on ground height, like ankle height. So it doesn't work in wetlands, and it doesn't work during hurricanes. So there's not many studies doing modern time prior unless you use a system like I developed for that.
So far, just one.
Just one, and
One data point.
if you want to send people to do this experiment and use my citation, that'd be great.
We don't generally get hurricanes here, but we do get nor'easters. And I was wondering, are you going to be trying to do the same kind of study with nor'easter kind of events, which can be quite damaging to the seashore?
Yeah, absolutely. I would love to, especially up at Plum Island. It's a beautiful wetland. So absolutely. When I was writing grants initially for this, I was very particular on saying high energy storms, not hurricanes, because any type of high energy could impact it.
Apologize for repeating each question, or not repeating the same question, but it seems like sedimentation in general helps to store carbon. And I have an interest in a local project where they've been dredging some little ponds, which I'm not too happy about because it would like insect loss and other life. And I'm also now thinking, because this seems to be a tactic used by municipalities to quote clean ponds, but are we also then creating a net emission of carbon by doing this dredging when sedimentation is actually helping to sequester carbon?
Yeah, absolutely. I mean, it goes into the fact that it's kind of all connected. The whole environment's connected. So if you dredge, you don't have to maybe add chemicals to stop those algal blooms or something. But adding those chemicals might change the acidity, how carbon reacts, how it's stored. So it's kind of a double-edged sword, I guess, that I can't give an exact answer to unless you have data showing it. But sounds interesting to collect soil cores and then do the dredging and see how it changes.
So if these storms they cause like the release of carbon like from the ground, so it almost is like a runaway effect. It's like more carbon causes more storms, which causes even more. So it like, is that kind of accurate to say?
Yeah, absolutely. That's perfect. That's what we call a feedback loop. That's exactly what I was trying to show, so good job. It's a feedback loop. If we have more storms, we're releasing more CO2, impacting climate, potential for that to happen again.